I will give right now an introduction into the CANopen application profile for Lift applications. I said I was at the beginning, at the start of the application profile, I was also responsible. I was in the group. I was working with some of you guys who are actually present right now on this specific topic. We have released the specification since then. We are now improved on the specification since then. But in general, the general principles doesn't have changed that much. The specification itself is divided in 4 parts. While part 1 is defining some general things as well as including the physical layer specification. We have in part 2 the virtual device definition. In part 3 the communication model, and in part 4 the detailed application objects. What does it mean? In the application profile, like in any of our application and device profiles, we have a definition of object 1000. The definition of the object 1000, the device type object, is important because that identifies us the device, that it is following a certain device and application profile. In some of the device and application profiles, we have also a definition on the error behavior, in this case on object 1029. In this case, in the application profile, we have that as well. The most important part is the definition of the PDO communication and the according mapping. I will come to that in a few seconds. As well as, and that's the most important part, on the application-specific data types and application objects. And sometimes we have also specific state machines specified. That's not so much applies right now here, but maybe that changes in future. What is the Lift application all about? What is the general idea behind it? The general idea is I have some kind of building. And in this building, I have a number of lifts in parallel. In the application profile, we have in maximum 8 lifts in parallel. And we have up to 254 floors. That's the whole application we cover in the application profile. Oscar gave us a short introduction into CANopen. What we've seen there is we have actually some limitations in CAN regarding the physical length of the cable. And we have limitations in the number of devices on a specific CANopen network. The cable length limitation actually depends on the speed I'm talking on. And in case of Lift applications, the speed is defined as 250 kilobit per second. And that roughly translates into a network length of about 250 meters. So how is it possible to cover a complete Lift application with maybe up to 8 lifts and 254 floors with 250 meters? Of course, it's not possible. So we need to think about to segment the network physically to make that possible. The same with the number of devices. In CANopen, we are limited to 127 devices. If we would have just one lift with up to 254 floors, we have already more than 127 devices. So we also exceed over that limit as well. So that means also from that point of view, we need to segment our application. And that's the general idea behind the Lift application. It needs to be possible to make segments on the lift and to put gateways anywhere in between where I would like to put them to make this segmentation possible. That, just as a start to think about, that is the general idea behind the lift. I have up to 8 lifts in parallel, up to 254 floors, and I need to be able to segment the whole network into sub-segments, into sub-networks, and all the information needs to flow freely from one segment to another, and I don't care if there is a gateway somewhere, and I don't want to configure maybe some gateway in between. On the other side, a lift application needs a number of specific devices to perform the function. Of course, if I'm going to a lift, I push the button. I expect that the car comes to me. Basically, with pushing the button, I call the car to me. The door opens, I go in, push another button, and the car goes to the requested floor again, and then I can leave the car. So what do I have? What do I need? I need the push button. The push button is what we call an input panel, panel in. Sometimes we have around the push button a light, or somewhere near the push button a light, which indicates to us that the car is actually coming into my floor. And that simple light is identified by the output panel. Even the indicator, most of the time on top of the door, which shows us in which floor the car currently is the panel output. And so the car is driven by a drive unit. The actual position is being identified by the position unit. We have, of course, controllers for the drive controller for positioning the car in the lift. We have a door controller for controlling the doors, open, close. We have the call controller, which handles all the calls. And of course, we have a panel controller. So that means we have all those different devices or functions, or as we call virtual devices. We call it virtual devices because we don't specify on how they are implemented physically. So we don't say this needs to be a physical device and that needs one. No, that's a market decision. As I said, with the panel, I have the button and there's a light. So we have one physical device, which normally involves a panel input and a panel output. So that means, that means I have one physical device. But a panel output could be also a separate device. The same is for the car door. With the car door, normally the door the door unit and light barrier is physically bounded together. So it makes sense that it is the same physical device. But it doesn't have to be. We haven't defined it. And of course, the controllers are normally together as one control unit and one physical controller unit. But it doesn't have to be. So that's the general idea behind the definitions in our application profile. We have all those functions or virtual devices, as we call it, as we have specified it, that perform a certain function within the whole lift application. There can be in a physical device and so on. Some of those virtual devices need to consume data. Some of those need to produce data. And that needs also to be defined. We need to define on which virtual device needs to consume or produce what kind of data. That's the communication relationship between those virtual devices. And only that makes us possible to have this kind, to have some kind of plug and play behavior. All those virtual devices have received certain numbers. Of course, we use those numbers technically to identify those devices. I said we have specified object 1000. Object 1000 indicates to us that this is a device, a physical device, dedicated to lift applications by reading the lower 16 bits of the 32-bit value, and the lower 16 bits read 417. That indicates a CiA specification 417. And yeah, I read the title, and then I know it's a device for lift applications. In the higher 16 bits, we have specified or we can identify the virtual functionality. So it's either maybe a direct device, a virtual device, a function like an output panel, or it indicates to us that this physical device supports multiple virtual devices. And if it's indicated that it supports multiple virtual devices, then we have object 6000, which indicates which of those virtual devices are being supported. And you can see a physical device theoretically could support up to 254 virtual devices. That said, we don't have that much. I said also, with lift application, we need to be able to separate our network segments by gateways. The worst case situation is that actually the gateway could be our interface to the complete lift application. So it represents the complete lift. To be able to do that, we thought about it, and we came only up with one solution, and that one solution is that the whole lift application needs to fit in the whole object dictionary of one physical device. With that said, we want to make it possible to support up to 8 lifts in parallel. And we have to put it in one object dictionary. For that reason, we subdivided our object dictionary into basically 8 parts, where the first part is representing our first lift, the second part, the second lift, and so on. And then within the range of one lift, we have all the dedicated functions. Like we have the definitions for the panel inputs, for the panel outputs, car door, unit, light barrier, and so on and so on. And that makes it possible that we can place a gateway anywhere within the segments, and any of those devices connected to any of those segments doesn't even recognize that the device is connected only to a subsegment. Like in this example, I have 2 segments, CANopen network 1, CANopen network 2, with a gateway in between. The control unit is maybe connected to network 2, and some I/O is connected to network 1. The gateway is either somehow a dump gateway. When it's a dump gateway, then of course we need to set it up to tell it what is being connected within the network. If it's an intelligent network, it may just scan what is connected on network side 2 and represents the functionality from network type 2 into the object dictionary to side 1, and the same vice versa. So it scans network 1 and presents all the functionality it found on network 1 onto the side of network 2. So that makes it possible to place gateways anywhere in the system. The gateway could also represent functionality which is not connected via CANopen, but via some kind of a proprietary network. What we also need to define is the communication between the different devices. We need, and that's basically our PDO definitions. And here we are faced with the very same problem. We have in CANopen, in a single device, we have available only 512 PDOs. So we have only the possibility, the limitation, to be able to transmit 512 PDOs and to receive 512 PDOs. And I said the gateway, so one physical device, could represent the complete lift application. So everything needs to fit into one physical device. So it needs to fit into the limitations of CANopen, and that's possible. We assigned the dedicated PDOs to the dedicated functions. We have a range of PDOs for the virtual input. We have a range of PDOs for lift application 1, for lift 2, and so on. And then within one range, you have the dedicated definitions for the PDOs, for a virtual output, like for the load measuring, for the car drive control and status, car position, car door control and status, and so on. And to give you a different view on this, we basically built a matrix, the communication matrix, where we defined our messages. In this case, I have, for example, defined message 3. We assign to that message 3 CAN identifier 181X. And we define that this message 3 is regarded as a transmit PDO or receive PDO 262, depending on what the physical device should it transmit or should it be received. And should it be transmitted or received basically depends on the functionality which is implemented on the physical device. And the functionality, the virtual device, is then, in this example, either the car drive unit or the car drive controller. So that means if the car drive unit is being implemented, the message is being transmitted as transmit PDO, or is it, if it is the car drive controller, it's being received as a receive PDO. And the content of the PDO in message 3, as you can see here, is in this case the control effort. Because the car drive unit transmits the control effort to the car drive controller, so that the car drive controller can basically control the drive. A physical device, as said, has implemented object 1000 to identify the physical device. We have object 6000, which indicates us the supported virtual device types. We have, as a configuration value, the identification to which actual lift number this physical device is assigned. We have our virtual input mapping, output mapping, and other specifics, which are dedicated to a physical device. And then on the other side, we have our virtual device definitions. And each of those virtual devices needs their own input-output data, process data, configuration data, and all these kind of things. So in this case, for example, we have our input panel unit where we have our input group values, we have our parameter for those definitions. And then we have our PDO definitions, which is for the virtual input panel like this. We have, I said we have a defined range of PDOs, in this case, PDO 130 to PDO 256, with the assigned CAN identifier 480 hex, plus the node ID of the physical device. And then in the virtual input, which I explained at the beginning, the virtual input is basically just a push button. It's just the push button to call the car. And this small little button tells us what type of button it is. It tells us, is it a standard call request? Like if it's an output panel where I just have this single button and which tells the system, when I push this button, tells the system that I want to receive the car on this floor. So this little button tells the system it's a standard call request. It's the source lift, like I'm positioned, I push the button on lift number 1. It tells me the source panel, the source door, like I'm on floor 5, because that tells the system I want to receive the car on floor 5, and it tells on what side of the lift I'm placed. And the same button could be also placed in the car or somewhere else, and so we have the very same definitions for all buttons in the system. The button could be also a more important button, like it could be a priority call, it could be a firefighter call, or something else, a VIP call, because with the button associated, it's maybe not a simple button. There is a key associated, which I need to insert in the button first, or I have a RFID key to be verified first, and all these kind of things. So we have all the complexity put into a very simple format. And that can be applied to any floor, to any side of the lifts, to any lift, and so on. And it's just transmitting this kind of information. And then the call controller can decide, depending on this information, which car should I send, how fast should I send, is there other calls which need to be processed before or not, is priority or not, and all those different kind of things. And then the message, for example, then looks like this. If I have a physical device number 5, then the CAN message would be 485 hex, and then the according number, which in this case tells me it's a standard call request here. Oh, I forgot sub function number 3, and then it's source lift number 1, floor number 5, door number 1, and yeah, function data. It's a standard call request basically. The same applies for the virtual output, for example, as a function, as a virtual device. We only need one CAN message. So we only need one PDO, because when that single message is being transmitted, everybody in the system knows what's going on. And this virtual output defines us, it tells can be transmitted by the call controller, and then it tells everybody which car is going where, or which car is placed where. So we can indicate if the car number 1 is currently going up or down. It tells us the floor number, where car number 1 is, or car number 5, and all this kind of things. It was just one single message. And that's been transmitted the very same way, like with the push button. And then everybody knows it. So even the lights around the push button know directly, should I flash because there is a car coming to my floor? The indicator on top of the cars tells me where the car is and where it's going up or down. And so I have all the information available. And the same is then true for all the other virtual devices. For all the other virtual devices, we define such functionalities for the PDOs to make it possible to do some kind of plug and play. Some kind of plug and play because someone needs to define or tell the push button which type of push button it is, at which floor it is positioned, at which lift, what the call controller should do with the information. What does it mean it's a priority call or not? What lights should go on? So there's still a lot of information to be set up by installing a lift. But it's not the communication that needs to be set up. It's application level information. Yeah. And here again, message. So that should give you a short glimpse, a short introduction into the CANopen application profile for Lift.